Hello everybody, Longo is back to show you a little bit about similar polygons, but we're going to just introduce it in this video, just kind of show you what's going on. So we're going to take an old school lesson, something we did a while back, and we're just going to dilate some figures here. So first two here, we're going to make one bigger, we're going to make another one smaller. So if you go back to what dilations are, what you're doing is you're scaling all of the coordinates by a certain factor. And that factor is called the scale factor. So what we're going to do here is we're going to scale this rectangle right here by a factor of 3. So that means this coordinate of 2, 2, we're going to multiply by 3, and all of a sudden that becomes 6, 6. And then we're going to take this negative 3, 2, multiply that by 3, and we're going to get a negative 9, 6. And then we're going to do the same thing with the other 2 points. So we have negative 3 is going to become negative 9, -9. And 2, negative 3 is going to become 6, -9. And if you were to connect the dots, you will see that this is going to keep the exact same type of shape. It's just going to be bigger. How much bigger? Well, the purple is 3 times the size of the red one. And some interesting properties are going to come up with that. So if you were to look at the length of the sides, so if we were to just count from negative 3 to 2, we would find out that this has a length of 5, 1, 2, 3, 4, and it also has a height of 5. So it turns out this rectangle is a square. But if we were to do the same thing with this, we should have lengths of 15. So to get from negative 9 to 6, that's definitely 15. And to get from negative 9 to 6, that's also going to give us 15. So all the sides of this square are 5, 5, 5, and 5, and all of these are 15, 15, 15, and 15. Because the scale from the little one to the big one is a multiplier of 3. Okay, so basically we're just showing you that similar polygons are not the exact same size, but the ratio of sides is going to be the exact same. Because this is 15, which is 5 times 3. 5 times 3 is 15. 5 times 3 is 15. You get the point. Okay, so now let's look at the next one with a scale of 1/2. Probably already know this one's going to get smaller. So 0, 0. Can't make that any smaller. 6, 0, half of 6, 0 would be 3, 0. And then this guy is 0, 8. Half of 0, 8 would give us 0, 4. And if we were to look, we're going to have another right triangle with its right angle at the origin. And now this one is half the size. Let's take a look. The original height of this triangle was 8, but now if we look at the height of the new one, it's 4. Go back to the original, the base was 6. Look at the base of the new one, it's 3. If you were to use the Pythagorean Theorem with the original, 6 squared plus 8 squared is equal to c squared. So 100 is equal to c squared. The hypotenuse of the original blue triangle is 10. And if you were to go do it again to find the hypotenuse of the green one, we would have 3 squared plus 4 squared is equal to c squared. So 25 is equal to c squared. So the hypotenuse of the green triangle is 5. So let's take a look. From the original blue one to the green one, 8 to 4, that's 1/2. 6 to 3, that's 1/2. 10 to 5, that's 1/2. The ratio of all the sides is 1/2 because that was the scale. As you can see, the angles do not change. In the original of the rectangle and the blown up one of the rectangle, these are all 90 degrees. In the triangle, this was a 90-degree angle in the green one and the blue one. Now, some of you might ask, how can you tell if this angle is the same measure as this angle? Well, to do that, you can find the slope. The slope of the green line right here is -4/3. And the slope of the blue line is negative 8/6, which reduces to negative 4/3. So you can see that even the slopes here are parallel. And if you go back to another chapter, corresponding angles are congruent. Okay, so the angles of similar polygons will stay the same, but the ratio of sides will be a consistent ratio from one side to the next. All right, so basically, let's see if you can determine, are these rectangles similar? So that's your job. So pause the video and you do a little bit of investigation and tell me if these rectangles are similar. There's a few different ways you can do it. I'll let you try your own way. Pause it, give it a try, click play when you're ready. Now, if you did this one correctly, you would have said that these are not similar. Now, there's a couple of different ways you could have done it. One way you could have done this is you could have found that this height is 10, and you could have found that this width over here again is 10. So the green one is a square. And now we're going to find the height and width of this rectangle. The height is 5, but the width is 6. So we have a green square and a purple rectangle. So those are not going to be similar. Another way you could have done this is you could have dilated one of the figures, because you see that 1, 1 and 2, 2. So basically the green one is twice the size of the purple one. So what you could have done is you could have multiplied 1 negative 1 by 2, and you would have gotten 2 negative 2. And then you could have multiplied this guy, 1, 4, multiplied that by 2, and you get 2, 8. But then when you get to this one, you have negative 5, negative 1. If you multiply that by 2, you're going to have negative 10, negative 2. And then this guy up here would give you negative 10, 8. So if you were to actually dilate the purple one by a scale of 2, you would see that the green one does not match up. So really there was a couple of different ways you can do this. I wanted you to give it a try on your own. So that's that. So if you answered they're not similar and had some sort of a rationale similar to that, you are good to go. This is Longo and I'm out. See you, bye.